At the very corner.
Yeah, he said they- He came in and was like, good morning. And nobody said anything. He's like, all right.
Yeah, you're the only one learned to be.
He's like, cool. He's like, we've had Christmas Mondays. Yeah, you do better. He's like,
All right, I think I got it, y'all.
yeah.
Okay, chapter 4 is called Study of Chemical Reactions. So if I mix two things together, how do you know that there was a reaction?
It bubbles.
It bubbles. What else? Heat's given off. What else? What?
Color change.
Color change. That's a big one. What else?
Be fit.
What?
We're just being petty.
Oh,
Change the state.
Synthetic.
you get a precipitate. Okay. So you kind of smoke. Smoke's kind of exciting. Fire. Okay. So those are all ways that you know that there's a chemical reaction. So have you been able to know that you got reactions in lab yet? I think you've only done one.
Yeah,
No, that wasn't a reaction. That was extracting out of
I haven't even
the
finished the
nutmeg.
last one.
Okay.
No,
Do you make aspirin like way at the beginning?
Yeah, that was a reaction.
Yeah. How did you know that reaction occurred?
Put two things
No, I
together,
didn't
you got a
know.
byproduct out of it.
Yeah, you got a precipitate out of it. Yeah. Okay. Okay. So on this, okay, what is the relationship between the following compound? Little practice for Wednesday.
I like that you roll with the chair.
You like that?
Yeah, you do that all the
Okay, I'll keep that in mind.
time.
I think I can make it draw it how I want. The little program. Okay, and everybody gets that there's hydrogens in all these spots. On chairs, we don't always write them all in. They're assumed on chairs. Chairs and boats. Twist chairs, twist boats. I'm going with 23. Is there anybody you know that isn't here?
Lindsay.
Who?
Jeremy,
Oh, yeah, Jeremy's not here.
he was.
Who was it? I hope you're not sick. All right, we're at 23. Wow, I got a lot of answers.
One of them's got to be right.
That's not
Okay, if you were to give me the name of that compound, what would the name of that first one be? Just as a way of doing it. Well, what would the name of that be?
Methyl cyclohexane.
Yep. Methyl cyclohexane. Agree? All right, what's the name of the second one?
Same thing.
Oh, it's the same thing.
So easy. I'm never more proud of myself.
That's an easy way to check for constitutional isomers. They'll have different names. Okay? If it was,
Oh, I missed
what's the name of that?
it.
No. Ethyl cyclopentane. Okay, wake up. All right. That would have been a constitutional isomer. Okay, so a good way to check for those is to do the naming. Okay, so now what is it? What's the difference between the chair and the boat? What did we do? We moved on single bonds. Do you want to answer something?
Yes, so constitutional is just like
No, constitutional is same formula, different structure.
how is that the same formula?
Methyl and ethyl.
No, it's not that.
This? Okay, what's the formula?
This is
C7H what? 2, 4, 6, 8, 9, 10, 11, 12, 13, 14.
I literally, like, you'd asked, I just would have got that wrong. There's no way.
Okay, what's this formula? C7H 2, 4, 6, 8, 10, 11, 12, 13, 14. You didn't even know that was the formula?
Well, I thought, I don't know.
Well, that would be something to practice then. Make sure you can do those things. Because that was from the first test. So, yeah, I think that we keep going. It kind of builds. Can I say? Okay. All right. So does everybody agree that A's out? Anybody not agree? I don't think anyone picked A. Okay. Now, how do you know if it's cis or trans? What does cis mean?
Same side.
Same side. What do you mean? What's on the same side? Okay. How many substituents do we have? One. How many do you have to have cis trans? Okay. Now, how do you decide if it's conformational isomers or identical? Okay, we're moving between conformations. It's D. A boat and a chair are conformations.
Why are they not identical?
One's a boat. One's a
Because they're conformation. They're almost identical. One is a boat and one is a chair.
Okay.
All right, all right. What if it was, instead of the boat, what if it was this? I'm trying to draw the hydrogens in kind of quick, so. Okay, what if it was that one? What would this one and this one be? No,
Confirmation.
they're conformational isomers.
Oh,
That's the difference between the chairs and the boats. They're conformational isomers. Remember, the whole thing was conformational analysis?
I think it has to do with the
One's a
equatorial.
This is pointing up. This is still pointing up. But we went from axial to equatorial. Okay. Okay. Do you want me to draw you one where it would have been identical?
Yes, I needed that.
Okay. Oops. Oh my gosh, here we go. You know me and the eraser. I'm gonna make it lower. There. There. I got it. I got it. All right, let's try to make it skinnier writing too. Okay. Do you see that this one is just this one flipped?
That's axial.
Okay. They're still, both methyl groups are still axial. These two would have been identical.
What did you mean by flip?
I took the whole thing and I flipped it upside down. Instead of doing a chair flip, I just turned the molecule. Okay, is that clearing stuff up? Okay, good. Oh, it still went. Okay. All right, how about this one? I only got two. I'll give you a couple more on Wednesday also. This is like the hardest thing for y'all. Okay, and it really is practice. So I'm making you practice. Okay. Well, it would be helpful for her life, I'm sure. All right, I'm going to hit the button. I want you to get counted. I guess it's better than no answer. Okay. Woohoo! Yes, it's constitutional isomers. Okay, so those of you who got it right, how did you decide? For those who didn't get it right, how did you decide?
Redrew it.
You redrew it? Okay. All right, so if you redraw the first one, it's going to be 1, 2, 3, 4, 5. Okay, and then where's this? Is it off of this one? It's off of this one, right? Okay, and if you redraw this one, it's 1, 2, 3, 4, 5, 6.
Don't we have two methods? I mean, not much.
This is the back carbon right here. I'll put a little B for the back carbon in my drawing. It doesn't matter. You can start from the back. Okay. Any questions on that one? Okay. Anybody figure out the formula or anything like that? Okay. Okay. So when studying reactions, some of the things we're going to look at writing the overall equation a little bit. You'll learn that we're not like real hyper about the whole balanced equation thing. We just worry about what happened to the organic molecule. Okay, because of course they're the most important. You know, I mean, where HCl ends up, we don't really care. Okay, to some degree. Mechanism. We're going to talk about mechanisms. Mechanisms is a step-by-step description of what the molecules are doing to get from here to there. Okay, you know where you're starting. You might know where you're ending. What happens in the middle? That's the mechanism. There's going to be bonds breaking and bonds forming to end up with your final product. A mechanism can be one step, just takes one little thing to get from there to there, or it can be 10 steps. Okay, so we'll start with simpler ones, so don't panic. But there are certain principles involved in writing mechanisms that I will repeat over and over as we go through the class. Okay, thermodynamics. Did you talk about that in general chem? Thermodynamics. Yeah, when you think of thermodynamics, what are you thinking of? Heat. That's good. Okay, thermometer, you know, heat. Do you remember delta H? A little bit of that? Okay, we're going to talk about that a little bit, but we're not going to calculate any of those. Dang, if you really like that. Yeah. All right, kinetics. I know you talked about that in general chem. Okay, yeah. We're not going to calculate any of that either. But we will talk a little bit about reaction rates. Okay, the main thing we'll focus on are going to be these. Okay, the mechanisms, because they're cool. All right. I can get this thing to work right. Okay, so we're going to talk about alkanes. So remember what alkanes are. They have no pi bonds. It's all what kind of bonds? Sigma bonds, okay? Alkanes are pretty unreactive. An old term for them is paraffin. Have you heard of paraffin in terms of wax? Okay, like if anybody ever make candles, ever do that? Where you buy the little thing and you melt it? No, huh? I'm sorry. It's kind of fun. You can have little scents and stuff, making pretty colors. Okay. Well, a lot of times what you buy is called paraffin. Okay. It means little affinity. Okay. The big thing that alkanes do is they burn. They burn. Okay. So if you take an alkane like methane, there's your methane, and you burn it. When you burn something, you're reacting with oxygen. Good. And everybody remembers oxygen's diatomic? Remember the 7 diatomic elements on the periodic table? You see here it is. My 6, okay? Okay, y'all know oxygen is 1. What about nitrogen? Yeah, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Notice that they make up 7. But is that 7? That's only 6. What's the 7? So that's kind of a little trick that you can use to remember that. Nobody ever showed you that? No. Good. I showed you something new, and it wasn't even organic. Holy cow. All right. Now, do you remember what you get when you take methane and react it with oxygen? You get CO2 and H2O. Any hydrocarbon that burns, which is most of them, you get CO2 and H2O. Okay? CO2 and H2O. Okay, there is one substitution reaction that they undergo, and it's called halogenation. Okay, so by substitution, we mean something is changing places for something else. Okay, so if you take something like methane and you treat it with a halogen, which is going to be, pick one, chlorine, okay. That's Cl2. Remember, those are diatomic, okay? What we're going to do is we're going to swap a hydrogen for a chlorine. So you're going to end up getting methyl chloride and HCl. You see how they swap positions. Okay? And we'll talk more about other compounds besides methane as we go. I don't know if I can. Okay, so the chlorination of methane, which is what I just wrote on that last slide. Do you want me to write it again? To make you happy to have it on the slide? Okay, so CH4 plus Cl2 gives CH3Cl plus HCl. Okay, now let me ask you this. Is it balanced? Yeah, isn't that nice? Okay, this reaction does not occur at room temperature in the absence of light. You have to have light or heat in order to get the reaction to go. It's required. Okay, there's going to be lots of reactions that have special things like that. If you don't heat it up and you just leave it sit at room temperature, it'll stay there forever, okay? It turns out that the most effective wavelength of light is blue because it is strongly absorbed by the chlorine gas. Now, I didn't mention that chlorine is a gas and methane are gases, okay? You get a high quantum yield. What that means is many molecules are formed for every photon of light absorbed. If I wanted to do this reaction, I would put methane and chlorine gas in the same container and I'd shine blue light on it, okay? And it would take a long time. Like it won't go unless you use the light, but it'd probably take like a week. So it's not a real good one to use in the lab, okay? Besides the fact that chlorine is kind of real poisonous. Okay, the mechanism involves what we call a homolytic bond cleavage. That means that the bond breaks evenly. How many electrons are in a bond? 2. Okay, so if you break evenly, each of the elements in your bond get 1 of the electrons. So this is an example of a homolytic bond cleavage. This one down here on the bottom. So 1 electron goes to A and 1 electron goes to B. Up here, this is heterolytic. That's actually the vast majority of what we're going to talk about in the year is going to be heterolytic bond cleavages. We're only going to talk a little bit. There's a couple of them that are homolytic that we'll talk about. Okay. the 2 electrons in the AB bond are both going to the B. So your B ends up negative and your A ends up positive because it lost electrons. Okay? Now notice the arrows. The arrows that are on this one, the heterolytic, is double-headed. Okay? These arrows are single-headed. Half. It makes a difference. A double-headed arrow stands for the movement of 2 electrons, the whole pair. If you're doing homolytic bond cleavage, you are moving 1 electron to one and 1 to the other. So you use a half arrow. You remember doing when you fill the orbitals with the electrons, okay? And do you remember that you use half arrows to do those? Remember that thing? 1s, okay? 1 is 1 electron, 1 is the other. They're half arrows. There actually was a reason, because they knew you were going to do this in the near future. I'm sure that's why it was like that, okay? Remember, a bond is 2 electrons. So if you're doing homolytic, 1 electron goes to one and 1 goes to the other atom. Whatever the atoms are. A and B are generic. They're not, that B does not mean boron. Okay. Okay, so what we're going to do involves those things that had these dots, these. Those things are referred to as free radicals. We talked about them a while ago. Okay, and this is called a free radical chain reaction. Because it's a chain reaction, that's why you get such a high quantum yield. One little thing and it just keeps going. Have you heard of free radicals in general? Like they're always talking about, you know, don't lay out in the sun because you'll form free radicals in your skin and that's what causes cancer, okay? Free radicals are bad things. Free radicals are what screwed up the ozone layer, okay? It's because one little free radical can cause a chain reaction and it'll just keep going. It's hard to get rid of them, okay? So there's going to be 3 parts to our mechanism. The first part is initiation. In initiation, you actually make the free radicals. That's what we're going to do first. Propagation is second. We're going to react with other molecules to form a new compound and another reactive intermediate. And then at the end, we're going to terminate. We're going to destroy any reactive intermediate still in the reaction mixture. So, first of all, these 3 steps, initiation, propagation, termination, are only for free radical reactions. They are not for heterolytic cleavage, okay? That is different, and there's a whole bunch of kinds of those. We're only going to talk about free radical chain reactions when we talk about free radicals, okay? The other thing is you don't go between types of mechanisms. Once you start on the free radical path, you stay on the free radical path. You don't then jump over to heterolytic or go between, okay? So right now you're going to focus on those little half arrows. They look like fish hooks. Would you agree with that? Fish hooks. Okay, so here is our first part. This is the reaction we're going to do. Methane plus chlorine gives a methyl chloride and HCl. And we're going to do the initiation step first. The initiation step gets the reaction going by producing free radicals. When we start out, we don't have any. Okay? So in order to get everything going, you have to give it the right amount of light. That will be perfect to homolytically cleave this bond. Okay? So notice that I drew my chlorine-chlorine bond and I put all my lone pairs on there. Okay? It helps when you do mechanisms to put the lone pairs in so you keep track of them. Okay? Now, I'm going to break that bond. So 1 electron is going to go to this chlorine, and 1 is going to go to that chlorine. Okay? So what did I make? I made a chlorine that has 3 lone pairs. And what did I just put on there? An extra electron, a free radical. Okay, does this free radical have a charge? Ooh, okay, what was the deal? What's the normal valence of chlorine? Look up there, what column is it in? 7 minus, how many unshared electrons are there? Yeah, 6, 7. And how many shared are there? None. Okay, 7 minus 7 is 0. A lot of people look at that and they're like wanting to put a charge on there because that electron is just by itself. Okay, like it bothers them. Like they feel like it should be negative. So calculate it until you've convinced yourself. Okay, all right, we just get one? We get 2 of them, don't we? I'll even make it these little mirror image for you. There we go. So we get 2 of them. Could you write a 2 in front? Sure. Okay. Now, it's important to understand that while we're giving the reaction mixture blue light, the right color that it needs, and the chlorines are breaking apart, they don't all break apart at the same time. Okay, some of them will get the right amount of energy and break apart, but there's still going to be a whole lot in that reaction mixture that have not broken apart. Okay, so we're talking about one molecule right here. We're not talking about all the molecules that are in the reaction mixture. Okay, because the percentage of free radicals at any given time in that reaction mixture is really little. Okay, it's not, if it was really high, it might like blow up or something. Okay, all right, so now we're going to propagate. That's it. That was all of initiation, getting it started. Propagation is a free radical plus a non-free radical gives another free radical. Okay, that's what we're going to do. So here's our free radical from the first slide, the last slide, I guess I should say. Okay, and remember how many electrons it takes to make a bond. How many? 2. Okay, we got one here, we got to get another one. So what happens is this chlorine and this hydrogen go together. Okay, now that's one of the electrons in that CH bond. Where does the other electron go, you think? Yeah, that's the only place it's got. We're homolytically cleaving it. Okay, so now what did we make? We made a CH3 that has what on it? It has a single electron. We made a free radical. Okay, and then what else did we make? Between the H and the Cl, we make a bond, right? So it's going to be like this. So we're going to get both of those. Okay, does that carbon have a charge? No. What's the normal valence of carbon?
4.
Okay, how many is it sharing? I'm writing it out. It's sharing 6. Half of 6 is 3. Okay, and how many unshared electrons does it have? 1. 4 minus 3 minus 1 is 0. Okay. So do that until you convince yourself. Okay. Okay, so now we started with not a free radical. We added a free radical. We made a new free radical and we got a not a free radical. Okay, so now what's going to happen is that free radical that we made, that methyl free radical, what is it going to do? It's going to find something else in the reaction mixture that is not a free radical. Okay, and that's going to be chlorine. Well, we made 2 of these to begin with, right? Where'd the other one go? What do you think? It reacted with a methane and abstracted a hydrogen and started another chain. Okay, so it's no longer there. Free radicals are reactive. They react right away, okay, as soon as they're formed. They don't hang out and go, I'm going to wait for that methyl free radical so I can react with it. That only happens as a last resort. So what's going to happen is this free radical needs another electron to make a bond. So look what we made. A carbon-chlorine bond. And what happens to the other electron in this double bond? Or sorry, in this single bond, these 2 electrons. It goes to the other chlorine. So what do we get? Okay, we got that. Did we get that? And we made a chlorine free radical. Okay, this is where the chain part is. Okay, because that chlorine free radical, let's see if I've got another color I can use. How about light green? Okay, this chlorine can go where? Up to here and do this step again. Okay, and it just keeps going over and over and over. Your propagation steps always make a cycle like that continues over and over. Are some chlorines still getting enough energy from the blue light that they're breaking apart? Yeah. But remember, that's a real small amount. All you have to do is get it started. Okay, so if you get it started and your light bulb burns out, the reaction will keep going. Okay. All right, so this is where your methyl chloride, your product, is formed in these 2 propagation steps. Okay. Now we still have free radicals in there, and so to get rid of them, eep, eep. There we go. We do termination steps. I can't wait to hear that on the video. All right, let me go back. I'll go back to yellow. Okay. Termination steps. This is where the free radicals come together because there's nothing left for them to do. They've all done their thing. We've made all the methyl chloride we're going to make. So this electron and this electron are going to make a bond. Hey, that's the product, isn't it? Okay, but what happens is that is not where most of the product is formed. It's formed in those propagation steps that we did in the last slide. Okay, now, what are all the possibilities? Those were the only 2 free radicals formed in the whole thing, right? Okay, so what are the possibilities going to be? We got a methyl plus a chlorine. What else could we have? A what? A chlorine plus a chlorine. Can you see those? Good enough? Okay. So this plus this are going to make some more chlorine. Okay. And lest you think that we're crazy people, they've done studies to prove that all this stuff happens. Okay. They really have. Oh, I guess I'll write it like that. Is that going to mess you up? Okay, and the other possibility is going to be a methyl plus a methyl, right? So this one and this one, making a bond. Okay. Remember, the concentration of free radicals is really low at any instant. So this is the basic, that's it. That's the whole mechanism. It looks like a lot, doesn't it? Because there's all those steps, okay? Remember that. The product is formed in the propagation steps. Initiation gets it going. Termination is what's left over. Okay, describe the initiation step in the halogenation of alkanes. Now I bet that the yellow won't work well. Okay, it was 23, wasn't it? Okay. Okay, initiation is making the radicals. Consuming the radicals is called what? Termination. When radicals are consumed and form, what's that? Propagation. The other things have nothing to do with it. Okay. Okay, so let's look a little more at a free radical. This is the methyl free radical. Okay. Your carbon on your methyl is sp2 hybridized. Okay, so remember that you have, write it out like this. Okay, you have 3 full sites of electron density, and then you have one site that's like got half what it could have. Okay, that's how come it's sp2. Okay, so you have a p orbital. This is the p orbital right here. Okay, and inside of it is an electron. Okay, it's in the p orbital. Whether you put it in the top or bottom lobe is irrelevant. Okay, it doesn't matter. Okay, it's important to realize that the carbon and the 3 hydrogens here are all in the same plane. Okay. It's flat, and you've got your p orbital. Okay, every free radical is like that. Those atoms are flat, and then you've got your p orbital with your electron in there. Okay, got that? Okay. Equilibrium constants. You remember that? Remember it was products over reactants. So everybody see the over part? Because I could type that, it was easier. Okay, but y'all understand it's the other way too? Okay. And I had a hard time with my physical science class. When I write it like that, they want to put it all on the same line. And then they cancel random things. Okay, so have you heard of delta G? Okay, delta G is Gibbs free energy. It's the energy available to do work. It takes into account the 3 properties of a system. Temperature is T. What's S? Remember S? Yes, it doesn't start with an S. Entropy. Okay. And what is entropy? Yeah, chaos, randomness, disorder. Okay. And H is enthalpy. That's the heat content. Enthalpy. Okay, delta G equals delta H minus T delta S. Why do you think temperature is with the entropy term? What happens as you raise the temperature? They move around more, right? So there's more disorder. That's all. Okay. You can look and find tables and calculate delta G by taking the free energy of the products minus the reactants. Okay, you probably did that. Okay. Do you know what the 0 means? Delta G 0. Yeah, that means everything's in its standard states. That's the state that it is in at 25 degrees C, and I think it's 1 atmosphere. Okay? Delta G0 equals minus RT natural log of the equilibrium constant. You remember that? Good, because we're not going to do anything with it. Remember what R is? It's a constant. Okay? Okay. All right, now this is the important part. If delta G is negative, the reaction is favored and the equilibrium constant is greater than 1. If delta G is positive, the reaction is not favored and the equilibrium constant is less than 1. Okay? Did you talk about that at all? Okay, all right, good, good. You're going to talk more about these again in biochem. You do actually do a lot of kinetics and thermodynamics in biochem because they talk about how the enzymes work. Okay. I'm like, oh, okay. Enthalpy and entropy, okay. Delta H0 can also be calculated by enthalpy of product minus enthalpy of the reactant. And again, you look them up on little tables. I have absolutely none of these numbers memorized except the things like O2 because those are 0. So otherwise I have none of them memorized. Okay. If it's exothermic, delta H is negative. If it's endothermic, delta H is positive. Do you remember that? What does it mean to be exothermic? What? Gives off heat. Endothermic takes in heat. Okay, we're going to use those terms again. So, and you can calculate delta S0 from tables too. Notice it's always products minus reactants. That's how I learned it. I kept getting it mixed up as a student, and I finally figured out it's alphabetical order, and then I had it. Did you figure that out? Or did you just get it? You might all just got it. Okay. All right. The enthalpy, the change in enthalpy for the chlorination of methane, if you go in and calculated it out, do you not have this? Oh, okay. I don't know. Or another page. Okay. Delta H is minus 105.1. Minus 105.1. What's important is the minus, because that tells you that it's exothermic. Okay. What else do I want to tell you out of this? Not a whole lot else. That's the main thing off of that. You can calculate out all those numbers. You could go look up methane and chlorine in tables and get them all and figure them all out. But we're not going to do that. Okay? We're not going to do that. Okay, so the next thing is the kinetics. Okay, so we'll start the kinetics on Friday. Okay? On Wednesday, we'll review for the test. I'll give you multiple choice questions. I'll answer questions. Whatever you throw at me, I'll do my best. Okay? And I'll see you tomorrow afternoon for the study session. At what time? 2. Because I have class till 12:15, so 1 would be hard for me. Because I gotta go eat because I'm not starving. Yeah.